strength of acids and bases, and the pH scale. So let's start with strong versus weak acids and a little bit on bases as well. So a strong acid is defined as a substance that is going to dissociate completely. And being an acid, it's defined as a proton donor or a hydrogen donor, gives up hydrogens. So strong acids completely give up their hydrogens. So you end up with a lot of hydrogens in the solution, and remember the hydrogens immediately grab onto water and form hydroniums. So we're going to be using hydroniums and hydrogens interchangeably, but really the hydrogens grab onto water and form hydroniums. So if we took hydrochloric acid, which is a strong acid, and we put it in solution. So imagine there's some water floating around, you've got some hydrochloric acid. If you put it in there, because hydrochloric acid is a strong acid, if you were to drop 3 million of them, or 3 gazillion, or whatever it was, of these molecules into water, you would end up with all 3 of them dissociating. So all of them would let go of their hydrogens would grab onto water and form hydroniums, and then the chloride would be left. The point is, strong acids completely let go of their hydrogens. All of them that go in let go of their hydrogens, or pretty close to all of them. Weak acids only partially dissociate. So if you throw in a whole bunch of them, some of them will let go of their hydrogens, but not all of them. That's the difference between them and strong acids. So acetic acid, we have a hydrogen on here which can get dissociated from the acetate ion. If you were to put it into solution, there's 3 of them, imagine there being 3 bazillion of them, some of them would dissociate. So some of them would let go of that hydrogen ion and would go off and grab onto a water molecule and form hydronium. So some of them have lost those hydrogens. However, a bunch of them don't do that. That's what makes them a weak acid. They stay together more often than they dissociate. Not all of them donate their hydrogens. Some of them still do, they're still acids, but not to the extent that strong acids do. Bases, same idea, but instead of donating hydrogens, they're accepting them. So strong bases fully accept hydrogens as much as they can. Weak bases, not all of them will accept the hydrogens. So just a proportion. For strong, a higher proportion of them will accept the hydrogen ions, or if they're acids, donate. And a weak base or acid, well, they will have a lower proportion of them doing their trading of hydrogens. So we can test out different compounds and see to what extent they do this, and we essentially end up with several acids that are very well known that will do this. So these are 6 of the strong acids that are very well known. And then for bases, generally the things with hydroxides on them you can consider to be strong bases. There's some that don't dissolve that all that well, but generally if they have a hydroxide on them, you can think that they'll be a strong base. Strong acids, you kind of have to memorize this list and you'll know that these guys here are strong acids. Any other acid that you encounter, you can just assume is going to be a weak acid. Memorize these 6, anything else will be weak. pH scale. Lowercase p, uppercase h, because of what it represents. It is the power, that's the P, of the hydrogen ion, that's the H. So really it should have a plus there, it's the hydrogen ion. So when you are dealing with solutions, the concentration of hydrogen ions, and remember, being lazy when we say hydrogen ions, they grab onto water and they form hydronium, but same thing, just being lazy. So the hydrogen ions are really, this should be called, I guess, the pH3O plus scale would be the proper way of doing it. It can range. That's the point. It can be, say, 10 moles per liter if you're dealing with a fairly concentrated strong acid, or it could be 10 to the negative 15. And that's a huge range, a ginormous range of numbers here. And we're talking about moles per liter of hydrogen in the solution. 10 moles per liter would be a lot. 10 to the negative 15 would be a very, very, very small amount. So a huge range in numbers for the actual concentration. So this guy, Søren Sørensen, basically said, okay, this range of numbers is too big, and one of the ways that we like to deal with huge ranges of numbers is we like to log them. And so what we'll do with these concentration of hydrogen ions is that we're going to take that huge range from, say, 10 to 0 with followed by 15 other zeros and then a 1, so huge range of numbers. If we put it into a log scale, that was Soren Sorce's idea, it'll be a lot easier to deal with this. And that's how we ended up with our pH scale. It's a logarithmic scale. Remember, lots of hydrogens means low pH. So if you have a pH of like 1, that means there's a lot of hydrogens in there. Few hydrogens gives you a high pH. So if you have a pH of like 12, that means there's not that many hydrogen ions, really hydronium ions, in the solution. And the scale is the middle of the scale is 7. So 7 is considered to be neutral. Under 7, that's acidic. Over 7, that's basic. Under a pH of 7 means there's getting to be lots of hydrogens. Over a pH of 7 means there's not that many hydrogens. And really, right at 7 is when the hydrogen ion concentration, really hydronium ion, is equal to the hydroxide ion concentration. That's the definition of neutral. Tends to be at pH of 7 under normal conditions. Change the temperature, that might change a little bit, but always if the hydrogen and hydroxide ions and hydroxide ions concentration are equal, that is neutral. Whenever we use square brackets, we're referring to concentration, and we'll talk about that being molar concentration. So here we're talking about the moles per liter of hydrogen ions is equal to the moles per liter concentration of hydroxide ions. That's neutral. If you have more hydrogens, it's lower than 7 and it's acidic. If you have fewer hydrogens than hydroxides, it's going to be a higher than 7 pH and it'll be basic. So here's the equation for pH. If you want to calculate pH, it is equal to the negative log of the concentration of hydrogen ions, which we know really means hydronium ions. And this should kind of make sense a little bit if you know much about logarithms. One is that this concentration is such a huge range of numbers for hydrogen ions. If we log them, we will end up with a much smaller range. And you'll notice that as the concentration gets higher, when there's higher amount of hydrogen ions, that's when it's acidic, the pH becomes lower. And that's due to it being a negative log scale. So based on Arrhenius' concept of hydrogen ions, which really means hydronium ions when they grab onto water, we didn't really know that they grabbed onto water, and so this is why we say pH is equal to negative log of hydrogen ions. If you want to be a bit more correct, you can say pH is equal to negative log of hydronium ions. Remember, again, something in square brackets for us is going to mean concentration in moles per liter. So let's try this one out. If you have a solution, this water here is at 25 degrees, and the concentration of hydronium ions is 1 times 10 to the negative 7 moles per liter, what is the pH? So you can take that equation you have memorized and say, okay, well, if I want to find the pH, I'm going to take the negative log of my 1.7 moles per liter. I'm going to put it in here, and I'm going to, depending on my calculator, I could put in a negative and then log and then number, or I might need to put the number in first and then log it and then take the negative of it. Figure it out for your calculator. Either way, you should end up with a pH of 7. It should also give you a hint as to how the log scale works. Alright, let's try this one. What if you had, oh, this is not neutral water, and that's not good. If you had a solution that had a hydrogen or hydronium ion concentration of 1.5 times 10 to the negative 1 moles per liter, which would not be neutral, just some other solution, this would actually be an acid, what is the pH of this solution? So, again, take your negative log, put this number in, and log it, make it negative, and you should end up with a pH of 0.82. That is how you calculate pH from concentration of hydrogen ion, aka hydronium ion.